Okay, what we're about to do is learn our first technique for integration, our first trick. And because what we're trying to do is we're trying to develop a bag of tricks that will aid us in finding antiderivatives. And finding antiderivatives is a little bit different than finding derivatives. Derivatives, in finding those, we have a set of rules, and we follow those rules correctly, and we end up with the derivative. With integration, it's a little bit more of an art form. So we're going to learn our first method, our first trick to finding antiderivatives, and it's called the substitution method. But before we do that, I want to say a little bit about differentials. Let's suppose that we have a curve here, this blue curve, and then we have a tangent right here. Here's the tangent, and it's got a point of tangency right there. Okay, so there's our point of tangency. Now, I want to find the slope of that tangent line. Now, remember, the slope of that tangent line is the derivative at that point. So let's look at it this way. We've got the change in x here. I just go over from this point a little ways, and I'm going to call that dx. And then I go up some right here, the corresponding amount. I make a right turn here and go up until I hit the tangent, and I've got the change in y. Now remember, the slope of that tangent, the slope, which we learned in Algebra 1, was the change in y over the change in x, which is exactly what this is. Okay, the change in y over the change in x. And of course that equals the derivative. Now it follows then that we could multiply both sides by dx. Okay, and we get this. dy equals f prime of x dx. Now this is what I'm calling differential form. And here's the thing. We've been using this Leibniz notation before, dy dx. And we've been told, okay, this is not a fraction, it's notation. But the thing is, you notice if we look at the derivative this way, it kind of behaves like a fraction. And what we do is we use what we call infinitesimals. We say, okay, let's suppose this dx is infinitesimally small. And this dy is infinitesimally small. That's what we're assuming here. It's sort of a different way of looking at it because we've looked at the limit of the difference quotient. Now we're looking at this thing of saying, okay, I'm going to write the differential of y, dy, equals f prime of x times the differential of x. And this is differential form. Now, this is primarily the form we use to get to the integral notation. Because think about this. If we have dy equals f prime of x dx, and I put an integral around both sides. Now, look, this is integration of 1. Think of a 1 in here with respect to y. See? Well, what do you integrate to get 1? I mean, what do you differentiate to get 1 with respect to y? Well, y. The derivative of y with respect to y is 1. So I can replace this side over here with just y. Okay? And then this side over here, I'm saying, well, what do I differentiate to get f prime of x? Well, I differentiate f to get f prime, right? So there we have it. So what we have now is we have y equals f of x plus c. And so you can see when we do this integration, we're using the differential form. Now, let's look at substitution. Let's suppose that we have a composite function. And remember, to differentiate a composite function, you take the derivative of the outside times the derivative of the inside. So if you put this in differential form, dy equals the derivative of this dx, notice the derivative of f of g of x is f prime of g of x times g prime of x dx, right? This is the differential form. Except, you know, this part right here is a little more complicated. Okay? Now, let's look at this. If I then integrate both sides, if I put an integral around both sides, of course, this left side is y, and here's the y. Here's the the right-hand side, right over here. Now this is kind of a mess, and we want to clean up that mess. In other words, I don't like the fact that I've got a g of x here and then a g prime of x dx here. I would rather just have f prime of x dx. Well, I can't use x, but here's what I can do. I can bring in another variable, and I can just say, well, let this variable u equal g of x. Now, I take that and put it in differential form and have du equals g prime of x dx. See that? Now, take a minute and just dig what we have here. See this g prime of x dx right there? And I have it right here. Well, du is equal to g prime of x dx. So I think I should be able to take g prime of x dx and just replace that with a du. And see this g of x? I'll just replace that with a u. So let's see what we have. We have this messy looking thing can be replaced with this. And now we have something that's a little bit tamer looking. Okay, now let's look at an example. Here, well, let me do this just so you'll see where everything came from. Okay? You can see where everything came from. Okay? So let's look at an example. Let's suppose that we've got this and we want to find the antiderivative. Now, here's the thing. We would be happy if this were just x to the 7th, because we could just use the power rule for integration, but it's not that. It's got this mess in it, x squared plus 5 to the 7th. We don't like that. So here's what we do. I'm going to replace this x squared plus 5 with u, and then I take the derivative, right? So I take the derivative of this in differential form. See? So I have du equals 2x dx. It's just like we had dy equals f prime of x dx. It's just like that, except now instead of y and x, we have u and x. See, here's the derivative, 2x. Now, if we doing that, notice what we have here. In place of this 2x dx, I can just replace all that with du. And in place of this x squared plus 5, I can replace that with u. So this whole thing up here, this whole thing right here, I can just write this way. See? I made that substitution, and then I can replace the 2x dx. Now, here's the trick with this substitution. Notice I let u be something with the idea in mind that when I take the derivative of that, that derivative will be the rest of what's in this integral. See? So I'll let u be x squared plus 5, and then du is 2x dx. So I'll let u be this, and then du was the rest of it. And that way I can turn this mess right here into this lovely integral, right? And then I can just integrate, use the power rule for integration. And if we want to, we can substitute back in, because remember u is x squared plus 5. I can just substitute back in and get 1/8 x squared plus 5 to the 8th plus c. And there you have it. There's an example of the substitution method. Okay, let's look at another example. Let's suppose that we have x squared plus 7 to the 9th. Okay. Now, this one is very much like the previous problem, but what I'm going to do is I'm going to let u be x squared plus 7. And then it follows then that du is 2x dx. Okay, now here's what we want to take note of. Immediately I'm saying, okay, I can make some substitutions here, but look at this. I've got x dx, and here I've got 2x dx. Well, that's unfortunate because I've got this 2 there. But notice what I can do. I can divide out that 2. And now look at this. Now I've got x dx here, x dx here. So it looks like what I can do is replace the x dx with du over 2. And then I've got u for just this x squared plus 7 to the 9th du over 2. And now I'll go ahead and factor out that 1/2. Yeah, like that. So now this is a real simple integral because what we've got is we've got 1/2 u to the 9th. And this is going to be 1/2. Let me just put the whole antiderivative in here. 1/10 u to the 10th plus c. There we go. So we could, simplify a little bit, and that's 1/20 u to the 10th plus c. And if we wanted to, we could substitute back in, although this is not required, and we would put in x squared plus 7 to the 10th, because that's what u was, plus c. And there we have it. So now remember, we also have, let's look at another example here. Let's suppose that we have sine of 5x. Sine of 5x. Okay? We don't like the fact that it's not just sine x, it's sine 5x. So that vexes us. So let's do this. Let's let u equal 5x. Then du is 5 dx. See? The derivative of 5x is just 5. So now, notice I've got this dx, and here I've got 5 dx. So just divide by 5. And now we've got this. We've got sine u du over 5. See? In place of the dx, I put du over 5. And I can factor out that over 5. See? Like that. And I get my antiderivative, which is 1/5. Now remember, the antiderivative sign is not cosine, it's negative cosine. And there we have it. I believe that's got it right there. And of course we can substitute back in if it was in our heart to do so. And we have cosine of 5x. There, plus c. Don't forget the plus c. And there you have a couple of examples. Now also remember this. Remember that e, if you have e to the x, remember that antiderivative is just e to the x. And so we could have a substitution problem involving e, maybe e to the 7x, see, like that. And then we could just let u equal 7x, du equals 7 dx, and du over 7 equals dx. See? Whoops, ran out of room there. There we go. So what we would have then is we would have this integral of 1/7 e to the u du. And of course that would be 1/7 e to the u plus c, right? And we could substitute back in if we wanted to and get 1/7 e to the 7x plus c. And there's your antiderivative.